Hello students, in this session, that is the S block elements part 1, we are going to discuss those S block elements which are in group 1 of the periodic table. We are going to discuss their physical and chemical properties along with their occurrence in nature and some of their important compounds along with their applications. If we look at the periodic table, then the elements of group 1 other than hydrogen, that is lithium, sodium, potassium, rubidium, cesium, francium, and later discovered unionelium have been included in the S block elements. These are also known as alkali metals because of the reason that they are metallic in nature, therefore the word metal, and their hydroxides are very strong alkalis, therefore the word alkali. Since the alkali metals are extremely reactive, they do not occur in free state in nature. Being the most electropositive elements, they are found in nature as cations, combined with the most electronegative ions of the elements which occur towards the right end of the periodic table. This table shows the occurrence of the alkali metals in terms of parts per million in the Earth's crust, soil as well as seawater. If we look at these values, we can see that sodium is the most abundant alkali metal, followed by potassium. Francium, being radioactive, is extremely rare. Even if we consider all the elements of the periodic table, sodium and potassium are the 7th and 8th most abundant elements in the Earth's crust respectively. The electronic configuration of the outermost electron shell of alkali metals is ns1. The large size, along with only one valence electron per atom, results in loose metal lattice formation by the alkali metals. Let us see how these factors affect the bonding in alkali metals. Scientist Lawrence proposed Electron See Model to explain bonding in metals. According to this model, there are islands or kernels of shielded nuclei in a sea or common pool of valence electrons. Among alkali metals, the sea is very diffused and the binding is relatively weak, resulting in weak metallic bonds. Thus, the valence electrons move freely from one metal ion to another without much difficulty. This model explains the various physical properties exhibited by the alkali metals. So let us first discuss the physical properties exhibited by alkali metals one by one. The first physical property that we are going to discuss is the atomic radius. If you look at the figure, the numbers displayed below each element are the value of their atomic radius in terms of picometer. We can see that the atomic radii are increasing as we move from top towards the bottom in the group. Lithium is the smallest, whereas cesium is the largest. This is because of the reason that the incoming electron is added to a new shell. In lithium, the outermost electron is in 2s1. The new electron which is added in sodium is accommodated in 3s. In potassium, similarly, the valence electron shell is 4s. Similarly, the incoming electron in rubidium is added in 5s, and in cesium it is added to 6s. So as we move towards from lithium towards cesium, we can see that a new shell is added each time. The increased value of effective nuclear charge is balanced by the increased shielding effect. In general, the alkali metals have the largest size in the periodic table. The next physical property that we are going to discuss is density. Due to large atomic size and weak binding forces in their metal lattice, the alkali metals exhibit low densities. On moving down the group, that is from lithium to cesium, the increase in atomic mass is comparatively more than the increase in the volume due to the addition of a single shell. So their densities increase on moving down the group. But this trend is not followed as we move from sodium to potassium. Potassium is lighter than sodium, probably due to much increase in the atomic size. Now, while we are discussing these properties, you must be noticing that we are not discussing the properties of francium. It is because of the reason that this radioactive element is extremely rare and its properties haven't been much explored. Melting and boiling points. In this figure, the dark blue bar shows the boiling point, whereas the light blue bar depicts the melting point. We can see in this figure that both melting as well as boiling points decrease as we move down the group from lithium towards cesium. This is because of the reason that the strength of the cohesive forces in their metal lattices decreases with decrease in their atomic size. Next property is the heat of atomization. We can define the heat of atomization of 1 mole of substance as the energy required to convert that substance completely into its gaseous atoms, or the energy required in total separation of all its atoms. In this state, all the bonds are broken and no new bond is formed. So the heat of atomization decreases as we move down the group from lithium to cesium. The intensity of color shows the heat of atomization of that substance. As we move down the group, we know that there is an increase in atomic size, which causes a decrease in the cohesive forces in their metal lattice. Therefore, the heat of atomization also decreases.